Hello and welcome back to another episode of the Reliability Game podcast. And you'll see us now in our brand new workwear. Will, I love this workwear, do you?
It's really good. I'm really glad we managed to. We've consolidated everything. We've got a standard together, and it's really nice. It's very.
I know. I think I said to you, didn't I? Image is everything. So if you guys are watching via YouTube right now, you'll see us. Again, we've been away for a while. We've had a lot of changes in our business. I'd say for the better in terms of where we're going, but sometimes the thing is about running a business, it's a roller coaster. It genuinely you just don't know. Like from one day to the other, your whole business outlook can change. And we're doing great. It's nothing bad, but it's just we've had a few personnel changes and a few pivots and stuff like that. So again, we've had to really jump back in. And I did say on the last podcast that I want to do this every 2 weeks. I'm not even going to say how often they're going to come now. So when they come, they come. But it's just we've had a lot to deal with. But we just said we want to come back and talk about some resonance, didn't we? We want to talk about some vibration things again,
Get back to the roots, get back to where we're coming from. And I think, talking on your point, I'm reading this book at the moment that I think you'll really like. And you realise that in life and in business, you're really not in control of a lot. And no matter how good we're doing or what we intend to do, something comes in that we can't control and just...
That's the thing. I think, being a business owner and having sanity, right, or, having the ability to be able to just live your life without that constant, what's around the corner, is just to accept the fact that we don't have control of what happens. We don't really know what's going to happen next. But you know what? As long as we're in the present moment right now and you're doing all you can to help your customers and grow your business and be able to give as much value as possible and as much insight, then that's all you can actually do.
It.
Do you know what I mean? And I think since I've started to have that outlook on life, my anxiety and my mental health has improved massively, because it's really difficult, especially when you're looking after, a team of people, and you're responsible essentially for everyone's well-being to a degree in terms of what you're doing. It can get on top of you, but I think sometimes it's just to let go a little bit and just to be able to say, do you know what? As long as I'm doing everything I can right now, then the rest will be able to take care of itself, as the universe says. So, resonance.
Yeah.
We've had so many, what we'll do, we'll talk generally on it, but we've had quite a few experiences that we'll talk with as well. I mean, we can't name any customer names for NDA reasons, but there's a few applications that I think, we've had some really, really interesting cases and some really easy fixes to problems that...
And hard fixes too, some really complex issues. I suppose as well, it's probably worth mentioning, obviously we're going to have people listening that may have an understanding of resonance, but if you're an engineering manager or you've got a plant, what sort of equipment can they expect to see these problems with?
Well, in terms of looking at, say, a plant, you can get problems with pipe work, you can get problems with motors, fans being a big one, generally quite a lot of mass on a fan that will rotate, in natural frequencies with fans can be, and critical speeds is very common, because fans in a process environment will run at different speeds or ramp up and ramp down due to processes which can interfere with critical speeds. Gearboxes as well. Yeah, a lot of people don't see. We had the issue with a very big gearbox actually. So gear resonance is a big one as well. And then when that happens, it can get really scary. You see. I think the particular case that we'll go over, that me and Will were working on about 2 years ago, was the highest reading I've ever seen.
Yeah, it was kind of like...
It was the highest. Yeah, it was literally no, this is definitely clear-cut spectrum. Nice, definite peak, but it was just the scaling that made me feel a little bit sick. And when I was on the vessel as well, the reading made me feel sick. The vessel didn't. But when you see these things, I think with resonance as well, the identification is quite easy to know, because you'll just feel like, oh my god, this is a little bit.
I suppose we should probably try and define for anyone listening what resonance is.
Yeah, of course. Do you want to do that?
Yeah, so
go on, Will, you go in
I'll
for it.
go for it.
Will's just done his level 3 anyway. So
Yeah.
anyway, just quick, not getting off the point or anything, but Will just completed his level 3. I took him through it, and he's loving life now in the vibration world. How much insight it teaches, and how that gets you to the next level of your learning is just incredible. And when I did it, but he's obviously embraced that now, and he's now on this level 3 journey as well as engineer. So congratulations on that, Will. Congratulations on that.
For anyone listening, resonance. So I'll try and explain this as simply as possible. But in the world that we live on, we've got structures and fans and bits of machinery. And these bits of equipment have a natural frequency within them. Is that kind of how
I would say every single object or even people have natural frequencies. And it's just the makeup of that matter.
And how it vibrates,
and how it vibrates at a certain frequency.
A bit like a bit like a guitar string or a piano note. You know, there's set frequencies. If I remember my music theory, like A on a piano, I think is 440 hertz that they tune the piano to. Don't quote me on it. I don't want to get in any trouble, but I think that's what it is.
You've got to check carefully that all the music files. No, that's not right.
But that is the natural frequency of that string, and it vibrates at that frequency. Now, what a resonance is if we take that natural frequency, whether it's that string or whether it's a fan structure, and we excite it by something else, potentially the machine running at a similar frequency.
Or external force.
Or an external force. Then that vibration, that will amplify itself.
It will. So you get 2 different responses, and what happens is them 2 responses then start to come into phase with each other. So you get the response frequency that's not existent until you excite it, if that makes sense. Then when you excite that frequency, then it starts to exist. That with the forcing frequency, right, the 2 waveforms add together, and what happens when you add 2 waveforms together? Amplifies, gets bigger. And when you get to a certain point with that critical speed, when they match, you then excite the resonant frequency of that structure or object. So you've got the response frequency, and then you've got the frequency imposing on it, which is a forcing frequency. It could be a speed, it could be the motor running speed, it could be external forces, or it could be something externally. So if I actually externally vibrate the guitar string or strike it, that's the external response. Then the natural frequency then takes hold, and then 2 frequencies add together that create that resonance, what creates the guitar string to vibrate viciously, that then gives the sound. So the 2 frequencies added together will create these phenomenons called resonance. And you've seen probably a lot of images, like the Tacoma Bridge one is a great one from the Mobius Institute when we're teaching the resonance, and you just see the bridge literally twisting and flexing the second mode of resonance as well.
If you YouTube the Tacoma Bridge, there's lots of content that you guys can go and have a look at.
Definitely, yeah. And then one of the methods that we do use to be able to detect resonance is bump testing, and we can use run-up coast downs as well. And usually what you'll find when you are going for a resonance is 180 degrees shift between the forcing frequency and the response frequency. So when you start to get into phase, into the middle part, that's why you get a higher vibration. And this is when you start moving away from the critical speed. For example, with a fan, it starts to vibrate less because the phase is actually then not in phase. It's starting to move out of phase with the response frequency. And as you move out of phase, the response frequency really dampens. Okay.
Yeah. And I suppose for anyone listening, like this vibration, when it starts going into resonance, can be extremely catastrophic, can't it?
Oh yeah, it can destroy machines. So when you do get this circumstance or this scenario, and what usually happens is something changes with the machine. So usually some form of maintenance has happened on the machine. Someone has tightened a bolt or something like that, or someone's actually altered the structure of the machine. Because how we actually alter the natural frequency of an object or a machine is either to be able to add more stiffness to that structure or add mass.
Yeah, and I think a great analogy to look at that is as you move up on a guitar, the strings get thicker, there's more mass on them, so the note has changed, the frequency changed, and then equally so, if you want to change that string's natural frequency as well, you would also tighten
it up, which causes stiffness. So that's what we got. So as we actually increase the stiffness of a machine, right, the natural frequency moves up. Okay. As we add mass to a machine, it actually moves down. So you've got this phenomenon of adding mass and stiffness. And then you've got something else called damping. So damping doesn't actually change the natural frequency of where it sits on the frequency scale. It just soothes what they call Q factor, which is the resonance factor of how much it will vibrate when them two frequencies get into response with each other. So it will just dampen the actual frequency, because some scenarios is really difficult to be able to change the natural frequency depending on what we're looking at.
There's some really cool stuff we did in Cat 3 on mass dampers in buildings and stuff like that.
I mean, you see these huge dampers in some of these.
Taipei 101 is a big one, I think, that's got a big one in there.
Big old and in the top of these buildings, these huge masses that are suspended on these kind of springs, and it's just like the engineering that's involved in them. Imagine, like, designing that.
Yeah.
Being responsible for that.
I think I watched
that's crazy.
A video the other day, and it was a big tower that was built in Central Park, New York, and it's a big residential. It was like a £250 million apartment.
Wow.
And at the top, though, they went up and they showed this mass damper. I kind of got a bit excited, and Judith, my wife, was like,
what? Yeah, we went over that level 3, Judith.
Yeah. So, but yeah, no, really interesting. But in terms of resonance wheel, you mentioned the fact, obviously, usually it's a mechanical change, like a maintenance-induced things, but what other things can cause resonance?
Well, I think anything that there's potential to change the mass of that structure or change the stiffness, because you have to think, why does resonance actually come into play after it's been okay? It's because the force and frequency of a motor or whatever's running is not matching the natural response frequency, right? And there has to be a change within that response frequency for it to be matched or come into play. Or the process has changed. So that means the force and frequency that is imposed onto the machine would have changed because of a process that's not usually there. And that's quite rare, to be honest, because generally machines will have a set process of how they run with a function. And that the process generally wouldn't change. But what you can get is external forces like pump cavitation or things like that potentially could come into play that weren't there before, that can then change the force and frequency. So you have to think of it as the force and frequency and the natural frequency. Is there anything that can change the force and frequency so it then matches the natural? Or is there anything that can change from the natural frequency, the stiffness or the mass of that structure, then can meet the force and frequency change? So when we're looking at especially fans, I mean, this is critically important for fans as well, because a lot of fans, especially in the malt industry, I mean, we've got a lot of malt customers and we've seen a lot of resonance issues with this as well, where what you'll have through the kilning process is different stages of different heat or airflow that requires the kilning process to be able to create the product. So what they'll do is restrict the airflow, which they'll restrict the speed of the fan on certain stages of where the fan goes. So a fan could potentially be running from 30% all the way up to 100, depending on what part of the kilning process they're in. All the kilner's going to get at me now and say, no, that's not right. It's just an example. So if we are, just base this on example. So say, for example, and every single fan as well has critical speeds.
So I suppose, you use the malt industry as an example, and we've seen this quite a bit. You've got this process requires the fan to run at various different speeds. Obviously, design is quite important then when it comes to fans.
It's hugely important, and we've even dealt with a lot of scenarios.
It's the reason I brought it up.
I know. We've got to be a little, end of the day, we're not going to name any names, but this is purely in the basis of just being to educate people in terms of understanding why the design process is so important.
And for anyone that looks after maintenance or is in the works of projects and stuff like that, it's something that should definitely be in the back of your mind. If you're putting in a new fan or you're involved with the project with installing a new plant that might have a bit of equipment, understanding the fact that resonance is something that must be considered in that process.
Hugely. And again, I think a lot of the time where you're looking at these type of processes, especially when you're looking at AHUs as well, because AHUs will, again, depending on what airflow is required.
Not very stiff structures, are they inherently?
No, they're not. And again, when it comes down to that, it's understanding where the natural frequencies are. So, finite element analysis is another technique that is used in terms of software programs.
From the design stage.
From the design point of view, to understand exactly what the natural frequencies could be and kind of trying to simulate the force and frequencies as well.
I think that's quite important to mention, is that we can't eradicate
It's natural.
It's natural.
This is laws of nature. This is what I love about engineering. It's about, the laws of nature will never be changed, right? We have to abide by these laws. Same as laws of electricity. We can harness electricity, right? And we can safely use it. And look what we've done, this civilization with electricity in terms of from the initial dark ages to where we are now, and even understanding it existed. Look how we've harnessed this beautiful natural kind of element to life, and how we've harnessed it into even this podcast right now, and how we're recording on computers, and how we've harnessed it is amazing. But it's the same with the natural laws of resonance, right? We don't want to mess with this, so we have to be really aware of it does exist. And we can't change it. Yeah. We have to work around it. We have to harness it. So the idea is of using these tests and, taking this seriously as well, because sometimes if we don't, the actual implications can be so catastrophic. I mean, we've seen like failures completely eradicate machines in terms of the destruction it can cause.
Quite scary. Like when we were on that vessel, like we were like, is this real? What we're seeing?
It is, and we could, even when we was on the vessel, we could feel it. You could hear it. It was a horrible pitch. It was a horrible tone. And when you compared that to the other engines on the vessel, you knew there was a problem. You knew that something was up. And when you've got machinery that's big and it's traveling at extremely high speeds, right? It's a health and safety problem as well. It's a health and safety issue in terms of what we're doing, because when we're on these plants, you've got these fans rotating potentially at 3,000 RPM, huge masses that are rotating at such high speeds. Like, the implication of if you do meet a resonance scenario, that fan will fail very quickly. And it won't be able to be detected quick enough to be able to be rectified if there is a sudden change in that structure, or a sudden change in that frequency. So the design stage, as we were talking, is so important to make sure that we design out any of these problems before they become issues. That's before even we can detect it, if that makes sense.
Yeah, because like we did this in ARP, like when it comes down to the design stage, doing these checks, doing these things like FMEA, they are going to cost more than if you weren't to do them. But as you move out of the design stage and into the implementation and commissioning, when you start finding these problems, the actual cost to rectify them out of design stage becomes even more.
But that's the thing, isn't it? Like, again, I was having a good discussion at one of my biogas sites with the plant managers there yesterday, and we're kind of on a mission in the minute to really try to change the culture of the whole company. I mean, he loves what we do, and he's kind of trying to get us on all of the sites. But it was almost trying to have this discussion at one of the sites that they've literally just built. They're literally just brand new.
Is this the one local to where I am?
Yeah, very local to where you are. And, the conversations about the fact that they're not even going to grid yet because of initial installation issues and problems. Wow. That, do you know what I mean? If we're rectified, they would be literally running now. Do you know what I mean?
I think design and installation is, definitely another topic for another podcast, but it's such problems.
Compliance testing as well. We can go over that. Acceptance testing as well. And this is where we can really help, because a lot of companies will accept things on the basis, it's brand new, without the tests done on them. And then if we can identify these problems well before they're there, it just saves so many problems down the long run, because essentially as well, if you have an acceptance testing kind of procedure, it allows you to be able to cover yourself when something isn't designed right. And I'm telling you guys, things... it's quite common that things are not designed correctly.
I mean, the one that we had with the AHUs, we were talking about resonance problems and laser alignment and belt alignment, and we were talking with these issues directly with the fan manufacturer, who didn't do FMEA, who didn't understand resonance, who didn't do laser alignment.
They didn't even vibration test these assets when they left the factory. And this is where... I don't know whether
due diligence with your supplier.
I think so, but I think I'm a little bit shocked sometimes, because I think I was usually on the assumption that these things were done.
Yes, I was.
Well. And then when I found out that these things are not even being considered, I'm like, what? Why?
At the manufacturing stage as well.
Yeah, so I think there's a level of awareness there, and it's not pointing the finger at anyone. It's just trying to say, well, how do we make industry more reliable? And that way, at the end of the day, it all starts at design.
Yeah.
Right. If design can be done correctly, then we don't have to intervene and do a lot of these things along the way. We don't even need to conduct the root cause analysis of why, because it was all in the design.
I think when we look at lots, good 70% of the problems we come across on a daily basis, it falls back to, that was poorly designed, or that was
poorly installed wrong.
Yeah.
Or they didn't think about how they're going to mount this thing. And, you know, even you look at majority of motors that are mounted in the plant, right? And you see how flimsy they are and how flexible they are. Do you know what I mean? This is another cause for a lot of resonance issues as well, because, you know, even the fact that tightening four bolts down can't be done correctly is a huge problem.
And I think, like, I don't think we're going to change design and installation anytime soon.
No way. That's a long game.
Hopefully this does is anyone listening who manages projects or manages a plant maintenance or anything like that has the thought processes of, I need to ask these questions when I'm getting something new installed, or have we considered resonance, or how are you mitigating that with your suppliers?
What experiences have you got in the plant? Because I guarantee that there's somewhere, every single plant we go to, it's like, oh God, when this particular piece of pipe work, it's always shaking or vibrating this way. And the fact is that a lot of these things don't get rectified until they fail. Do you know what I mean? And it's like, you know, quite clearly there's issues with these particular problems or resonances on site. And if you have an asset that is, you know, vibrating a hell of a lot more than all the other identical assets, there's some resonance problems somewhere within that particular plant.
And the nice thing with resonance, without getting too technical, it happens at usually lower frequencies, usually. And so if you have got assets, you're going to feel the vibration. You're going to feel like if you're in a building and you can feel the floor in your office shaking, something's probably resonating
out there, exactly. So I think it's about identifying if there is resonance, and if, you know, to be able to do that, you need to have some form of condition monitoring or vibration testing anyway to identify there is a problem, or, you know, generally you'll know about it if it's a bad resonance, or you may not, because if you've got hundreds of assets on site and you're not able to check every single asset, or you haven't got routine PPM inspections where someone checks these things, you may have these issues or problems happening, you know, without you even really knowing. And when that is the case, then these things will fail before you know about them as well. So having a good routine, you know, condition-based maintenance, you know, practice is key. And then when you do find issues or problems, it's not assuming that them issues and problems are imbalance or looseness. It's then doing the actual checks that allow us to be able to identify a resonance issue and problem without having to then rectify all of these things then to realise, oh, it's a resonance problem. So the idea is, you know, when we go anywhere and we do see excessive vibration, there's certain key indicators to look out for to understand there is a resonance issue as well. So the things that we do really want to look out for is really high vibration in one axis, okay? So resonance is very directional. Usually you won't see high vibration in all three planes when you're seeing a form of resonance. You'll see extremely high resonance in one direction and fairly low in the others. That's a real good indicator of a potential resonance issue. Obviously, high one times is where you'll find the resonance, because usually what the critical speed is
running speed related, isn't it?
It's usually the running speed that is then obviously coinciding with that response frequency. So
that can be also a really good test as well. Like if you are suspecting a resonance, you don't have lots of complex vibration analysis equipment. What you can do is usually it's to do with the 1x or the running speed of the machine. So because resonance is directly related to that, if you turn the machine off, that vibration should dissipate very quickly.
Very fast,
Compared to, say, an imbalance where the mass is always there. There's always an imbalance. As it runs down, the vibration is slowly dissipating.
Remember, with imbalance, speed is proportional to vibration, so it's linear. So if you've got a slight imbalance, even at lower speeds, you should feel that one times going around. It'll be a slower rate, but you'll see that vibration. Usually what you'll find with a resonance scenario is the machine will be fine up to like 70%. It'll be running sweet as a nut. Then as soon as you get to a certain frequency, which is obviously the response frequency resonating with the critical, it will start shaking crazy. And you'll be like, whoa! And you'll notice that as well through all fans that are ramp up, because every fan will have a critical natural speed. And, you know, you'll be going through different modes of resonance as well.
As it ramps up to its speed,
there's different modes of resonance as well. That's kind of getting a bit more technical. But when we're looking at, you know, critical speeds, you'll get through a first critical, you'll get through a second critical, and generally you'll then start to get to your running point of your machine, depending on how fast that fan is moving, whether that is. And the idea is at the design stage, the fan manufacturers should be understanding where that fan should be running at, and then understand where they should stiffen the structure to ensure that the first and second critical speeds are nowhere near it. Well, 20% away from any critical speed is the standard, so to speak, as well. So again, if that hasn't been done and there's a random element of, I don't really know, then you're quite likely to be potentially running at a resonance speed, which is then going to cause your machine to vibrate and fail a lot quicker than it should do. And that's all a part of reliability again as well, isn't it? It's understanding that it exists and trying to make sure that your machines run as smooth as possible. Do you know what I mean? And I think this is the thing as well, even trying to get to trim balancing and get your fans operating as low as possible. Like this is something that I didn't really consider when I first started, and it was a bit like, oh well, it's not vibrating too badly. But it's the idea of, okay, well, are we actually improving reliability here, or are we not? And it all depends on the ethos on site, because sometimes, you know, it's great to have that reliability mindset, but if you're at a site that has
and you're
a million problems, do they really want to trim balance a fan down to 5 millimeters per second to 1, for example? That's the least of their concerns. So it's got to be proportional to the problems that you have on site. But again, if we are reliability engineers, we've always got to have that view to improve machinery. So it's always really difficult
it's just taking steps at a time rather than trying to do everything at once.
I mean, that's I think when we first started, we probably tried to take customers
too much on a
hyperspace mountain, like from 0 to 100, you know, very quickly. It's because we love what we do and we're passionate and we see the end goal. But now I think we've learned massively that you have to approach it so differently depending on who you're dealing with, because, you know, a lot of the guys, I think as well, engineers, of course they want a reliable plant, but it's just they've got other concerns and priorities at that point, and how can we help them with them priorities as well?
I suppose to round it all off, I guess, resonance, though, is a high priority.
It's huge. It's massive. So whenever you do have a resonance, it's like it has to be solved straight away. So when looking for resonance, so I got off point there a little bit. Like, please bear with us because we do go on tangents. God. So when looking for resonance as well, we're looking for really high vibration in one direction.
Yep.
Usually you'll find resonance is very directional. Okay, as well, what we are looking for is extreme increases of vibration over small areas of speed increases. So you're looking at that huge ramp up over small periods of time. You're looking for machines that seem to be fine at certain processes, then other processes you're getting really high vibration responses as well. So yeah, anything else to add on that, Will, in terms of what we're trying to find?
I think that covers the most common things that we look for. Obviously, there's other more complex resonances, but I think for anyone that's got a bit of we've got that machine that gives us a few problems, those are the points to go look for to see if it potentially might be a resonance.
So let me try to test Will's level 3 knowledge a little bit now.
Oh gosh, here we go.
Put him on the spot. So if we are VA engineers, not just normal engineers, what tests can we do to be able to detect resonance?
So as VA engineers, the most common test that we usually employ to confirm for a resonance is a run-up coast-down with a tacho. We want to use that to get a phase reference to understand that when we go through a critical speed, are we getting a 180-degree phase shift?
Of course,
That's what we like to use. A good test for guys that don't have that equipment is, like we said earlier, you know, cut the speed, see if the vibration disappears very quickly. But once we've confirmed that we have got a resonance, we can then go to bump testing to try work out what part of the structure may be resonating. Usually it's structural, but with the gearbox, it was a gear, wasn't it?
It was actual gear, yeah, exactly. So again, that's another thing. With the tacho and obviously the run-up coast-down is really, really good test to confirm it, because when you go through that response, basically the response frequency and the critical speed or resonance or force and frequency, they will match and be in phase. But as you go through that period, it will lag, then it will lead, and it will go through that 180-degree shift. And basically what we're doing is with the tacho is just measuring the relative, well, not the relative, the absolute phase difference between them two signals, if that makes sense. And when we go through that, that's complete confirmation. But sometimes you'll get machines that ramp so quickly or shut off so quickly, that's really difficult to be able to capture that actual resonance scenario between the two. So that can be a really difficult scenario as well. And we've had instances where we've not been able to even capture it because how quick it stops or how quick it ramps up. If it's not an inverter, it's very difficult to get them events in as well. So another thing, obviously, just to add a few points on the bump test, bump testing is really, really good. And all we're doing is putting a force and frequency, hitting something and seeing what the response is. And all the responses is that machine vibrating at its natural frequency.
We're hitting it with a special hammer, essentially, that connects to the analyzer. And when we do that, we're able to inject frequencies at all the frequency range.
Yeah, and then we're going to basically here looking to see what the response is across a frequency range. And that response will allow us to understand how was that machine vibrating from that response at its natural frequency. So once we've taken that natural frequency, we can have a look at the force and frequencies imposed on it, whether that's running speed or rotational frequencies, and we're able to then see, do they coincide or do they not? So that's another method as well. And trying to think of any other tests that can be done.
That we do. I mean, there are other things that you can do, like bump testing when it's offline and stuff like that.
You can, yeah. We've never really done
online,
We've never really done that type of thing. I think it's called it's like reverse bump testing when the machine's running, and then you can kind of do tests. But we've never really been in the scenarios we've done.
I think
them
they're
tests.
the two core tests that we would want to try and do if we were looking for a resonance issue.
100%. But again, we haven't always got the tools for these type of
you have
equipment.
to work with what you got.
Yeah, exactly. And again, if anyone needs any help with these issues or problems, get in touch with us, because we love problem solving. I love a resonance issue, if I'm honest. Like, I love data collection where you've got mass data collection, but I'll be honest, when you're looking at just one machine,
just trying to solve a problem,
and you're trying to solve it's really exciting as well. So, guys, thank you for tuning in to another podcast about resonance. I hope you guys have enjoyed it. I don't know really what we're going to go on next.
Don't know. Maybe do a poll.
We'll do a poll. We'll get some ideas out there. What do you guys want to hear? You let us know. Anyway, guys, thank you for tuning in. And hope you all have a great week. We'll catch up with you soon.